convert the denary number 189 to hexadecimal. So if you're not familiar with hexadecimal, it is essentially the combination of letters and numbers to make up a number, and it uses the base 16, which is indicated by the name, because we have hex, which means to the base 16. So if we use this logic that it's to the base 16, we should automatically see a denary number like 189 and divide that by 16. And doing that, we get 11. And one important thing to note is that when you do this, you don't leave it as a decimal, you leave it in a remainder, because we will use the remainder to work out the other half of the number, or the hexadecimal. So we can use this chart, which is the conversion table, which is fairly easy to remember. It goes from 0 to 15, and for all the single digit numbers, it's all the same, as you can see. And once we get to 10, it starts going up in letters, but it starts from A. So we have A, 11B, 12C, etc. And it goes till 15. So doing this, we can just match this up. So we've got 11 and B. So we can do B first. And we've got 13. So 13 here is D. So the answer is B, D. Perfect. Convert the unsigned binary number 1010101111 to hexadecimal. So to do this question, the most important thing we need to do when converting from binary to hexadecimal is group up the numbers in groups of 4. So you would do from the right hand side, you do these 4 numbers, and the remainder of what's left. Once you've done this, you just convert this back to denary. This is the way I do it anyways. So to convert to denary, we use 8421, and we've got these numbers, so we just add these up, and that will give us 15. And we can do the same for the other 2 groups of numbers. We've got 10, and we've got 2. Okay, now what we need to do is we need to bring back the conversion table from earlier, and we'll just match them up. So starting from 15, we've got F, so we can do F, and then we go to 10, which is A, and 2 will just be 2, so it's 2. And that's your answer, 2AF. Okay, next question. Negative binary values can be represented using either sign and magnitude or 2's complement. Convert the denary number -107 to an 8-bit binary number using sign and magnitude. So for this question, it's using sign and magnitude rather than 2's complement. So sign and magnitude essentially uses the largest column, as in the largest number in the column, as the indicator of whether the number is positive or negative. So putting a 0 in this column will make the number positive, and putting a 1 in the column will make the number negative. So we can put a 1 there because it is a negative number. And now all we need to do is use this part of the table to make 107. So we start always from the left hand side, and can 64 go into 107? Yes, so you put that in. 64 plus 32 gives 96, so that will work. 16 plus 96 is 112, which is slightly bigger than we need to be, so that will be a 0. 96 plus 8 is 104, so that is okay. Can put a 1 there. And 104 plus 4 will give 108, so that does not work. 104 plus 2 gives 106. And 106 plus 1 gives 107. And that is the final answer. Next question, convert the denary number -107 to an 8-bit binary number using 2's complement. So, differently from the last question, if you notice any change, we've got our numbers that we're going to use to convert the binary number, and the difference is, in 2's complement, is the leftmost significant bit is automatically negative. In this case, it's -128, and this essentially indicates whether your number is negative or positive. If it's positive, this is a 0, and if it's negative, like in our case, it's a 1. Now what you need to do is from minus 128, you need to add the rest of these numbers until we get minus 107. So we need to work our way up. And in doing this, we can have a look. So minus 128 plus 64 gives minus 64, which is far too large. So this is going to be a 0. Minus 128 plus 32, I can't work that out in my head, but it would certainly be larger than minus 107. So that's going to be a 0. Minus 128 plus 16, I assume it gives minus 112, which we can still work towards. So we can put that as a 1. Minus 112 plus 8 would give minus 104. Not ideal, so 0. Minus 112 plus 4 gives minus 108, which is fine. Of course, we can't do 2 because that will be minus 106. And we add a 1 to make it minus 107. And this is your final answer, just as it is. Give one advantage of storing values using 2's complement instead of sign and magnitude. So, first reason could be calculations are performed easier in 2's complement. It allows for a larger range of numbers to be stored. No additional hardware is required for 2's complement. And it only has one representation of 0, which can make things easier. Okay, describe what is meant by the term character set. So, a character set is a list of characters that can be understood by the computer, and each character is given a unique binary code which is stored instead of the actual character itself in the computer. Convert the hexadecimal number 66 into a denary number. Show your working. Okay, so with this type of question, it is important to note that this might look like a denary number, but it can very well be a hexadecimal number. All we need to do is split the 6 and 6, and we go on from there. So we kind of work our way backwards. What we would do is times this 6 by 16, which gives 96. And then with this 6, you just add it onto this 96, which gives 102, and that is your answer. State 2 reasons why a programmer would prefer to use hexadecimal numbers rather than binary numbers. So the first reason would be that hexadecimal values are shorter than binary. So 1 hex represents 4 nibbles, which of course is more efficient. And the second reason is because hexadecimal values are faster and more reliable to read or write to. Okay, convert the hexadecimal number B7E to a binary number. So again, we're going to use this conversion sort of chart just to help us. And we're going to split this up as we did in the last one with 66 into 3 separate ones. Okay, so for E, this equals 14 on our chart, which also equals 1110, which as you can see 1110 gives you 8 plus 4 plus 2, which is 14, which can be seen here. Okay, now for 7, we can do the same thing. We can look at it here, and all we need to do is find 7, which is 4 plus 2 plus 1. And for B, which equals 11, we can do 1, 0, 1, 1. And put them all together with B first, 7 after, and E last. And this is your answer.